Yeah.
Go 5 centimeters.
All right. Great. Before you begin, if I could get you to clip this about mid-chest and. Okay.
Excellent. Here?
If you don't need anything else.
Excellent, thank you.
I'll just
Okay. Yeah, I'll do that afterwards. It's brilliant. I'll stand here so that I can. Put a shorter title than the one I sent.
The other title was
Yeah. Yeah.
How do you say, Montreal or Montreal?
Montreal.
Montreal.
Yeah.
That's what I say.
Yeah, that's, you say it right.
But when I go there, I don't understand the French.
It's very different. The pronunciation is very different. I mean, of course, the slang is very different, but formally, it's French. But it's hard to understand if you know European French. It's very different sounding.
And then I was young. I don't know if you were there. You were born at all. General de Gaulle went to Quebec.
Right, that was just before I was born. That was before the
sentence.
Vive le Québec libre, and then the
Free,
yeah, free Quebec, yeah, and then got a lot of people very excited.
You know the Colloquium speaker?
Hi, pleased to meet you. Mr. Exeter. Yeah. Yeah, I won't talk about it, but I can.
Oh yeah.
Yeah.
I don't like it.
Yeah. Oh, this is going to be the messy stuff today.
Has arrived to wherever we go after that. Yeah, so the spots are great. Just, do you have a car? Okay, then I also have a car, and I'll take her actually home. But my car is still somewhere behind. Remember where it is? But I can't ride.
Hello everyone. So before today's colloquium starts, I would like to ask for your help about the colloquium in 3 weeks. You probably noticed that the one that in 3 weeks is still open, and we need a speaker. Please volunteer or recommend local speakers. Thank you.
Thank you. It's my pleasure to present Carlos de Silva. Carlos is an international person. He was born in Mexico, got his PhD in the US, in Minnesota, University of Minnesota, with Paul Barba. I don't know if some of you know, probably not. And then went to Cambridge for a postdoc, was there for 7 years, and then went to University of Montreal. He's there for 11 years, so it's really international. And if you know, I don't know, some of you may not know, but because they come from a different globe, part of the globe, but Canada is French and English, and Quebec is French, and the rest of Canada is speaking English. And so I asked him, what are the classes that you talk, in English or French? And he said that I talk French. I thought I'm teaching in French. And so then he knows Spanish, English, and French. He can be a CIA agent.
I also have several passports.
That's American.
And American.
Yeah. And French and Quebecois.
So today Carlos will talk about two-dimension mapping of excitons in organic, but he will tell us also about inorganic.
Yeah. Thank you very much. First of all, thank you, Vali, for the invitation. It's been a great pleasure to be here and talk to many of you. I know, of course, very, very well the work of Vali and have followed it for a number of years, but it's been very interesting to see the diversity of work here. And so it's my first time to the University of Utah, although not my first time to Salt Lake City, and I'm sure it won't be the last time. So what I'm going to talk to you today about, it's a combination of a body of work that we've done really over the past 5 years or so, trying to address a relatively basic materials polymer science question. So in this field of polymers for optoelectronic applications, systems are fairly complex. We have polymer films with very, very complex microstructures that can vary quite dramatically depending on processing conditions, how you make your film, depending on materials properties like molecular weight of the polymer, and so on. And so the people who are interested in making applications with these materials might be interested in understanding, can we, from a very, very simple measurement, at least correlate just microstructure and device performance, but using a simple optical probe, like absorption or steady-state photoluminescence. So some of the work that I will be talking about has been this development that we've done in collaboration with an excellent theoretician called Frank Spano from the University of Temple University in Philadelphia. And then I'm going to then go on to present a body of work that has been relatively recent from somebody who you know very well, I presume most of you, John Lupton, who used to be here up to a few years ago, where he has very, very interesting and very compelling data that says, is this really the main way to think about optical spectra of these materials using these rather simple models that we have been participating in the development of, given that when you look at single molecules, when you do spectroscopic measurements using single molecule spectroscopy, the kind of inhomogeneity that we get and on an ensemble measurement of single molecules, and depending on what the structure of the chains are, the kind of bulk-like spectra that we can build is really purely explained by the fact that these are such inhomogeneous systems. So then what I'm going to do in the end is show some techniques that we've developed to look at in some detail interactions between or correlations between different optical transitions in these types of materials. But importantly, for the purposes of the colloquium that I'll give today, can we, in the film, in the solid state, have a very clean measurement of homogeneous line widths, so the quantum dynamics of the optical transitions measured through homogeneous line widths, and how do they compare to the single molecule homogeneous line widths that John Lupton measures? So this is what the colloquium will be about. I'm going to just briefly give you an overview of the kind of things that we do. This is related to what I'm going to talk about, but not the same subject. A lot of what we have been doing in the last few years has been trying to unravel the physics of photocarrier generation in these organic materials. The issue is that these are systems in which it should be very, very costly in terms of energy to generate photocarriers, because these are systems of very high binding energies. You can separate charge in heterostructures of these systems rather efficiently. You can induce charge separation. But to then generate actual charge carriers from this really should cost a lot of energy because of Coulomb interactions, which are very strong and so on. Nevertheless, it's been shown that in the order of 100 femtoseconds, you have very efficient generation of actual charge carriers. So what's the mechanism? So we do, I'm not going to go through the details because this is going to be very related to the technique that I'll talk about later in this talk, but we do coherent nonlinear spectroscopy detected through photocurrents. So we have devices that we excite with a sequence of femtosecond pulses that have a very well-defined phase relationship, read out the photocurrent anywhere in the IV curve, and measure 2D correlation spectra to try to address these sorts of issues. Another thing that we do in my group is trying to study the physics of potentially spontaneous coherence formation due to strong exciton-photon coupling in optical microcavities. So here what we have are Fabry-Perot microcavities, in this case made with organic materials, but we study as well quantum wells. So we study gallium arsenide quantum wells as well, and Fabry-Perot microcavities of these. And whenever you design an optical microcavity so that you put your photon resonance, so the dispersion, photon dispersion in an optical microcavity is quadratic, and you tune your microcavity so that somewhere around here it would intersect with the resonance of the exciton. You're coupling in a strong way the exciton and the photon that is strongly confined in the microcavity, and you make what you call cavity polaritons, which depending on the design of the microcavity and the properties of the exciton, can be in a really significantly strong coupling limit, so that essentially in gallium arsenide you can show that at 4 Kelvin you can form something that's akin to a Bose-Einstein condensate. So this emergence of spontaneous coherence in gallium arsenide, can we do that not at 4 Kelvin, but what I say, what the minimum temperature that would be acceptable to do an actual application of this would be Montreal in January. You know, if it can work in Montreal in January, at least that's what we should be. That should be our minimum requirement. And so for that, there's interesting possibilities with organic materials, and I won't get into the.
Did you say that was 95 absolute with the temperature?
Yeah, right. So, you know, last year we didn't go above minus 20 for about 6 weeks. So it can get cold. Last year was unusual, but so we do this type of correlation spectroscopy to look at polariton correlations. How do they exchange momentum to then drive themselves down to the ground state in this emergence of spontaneous coherence? What I will talk about today are this issue of microstructure in a polymer film and properties. So this is a perennial issue in the materials physics, the polymer physics in this field, is we can have quite complicated microstructures. And how can we go from, I mean, this is the length scale of our devices. Here we're looking at transistors. Here's a solar cell. And of course, they're flexible because we like to say we could print them and blah, blah, blah. This is all the sort of things we write in the grant proposal. But really the issue is these are very tunable materials, very, very easily tunable materials. So the device function is what we care about, but when we look at the materials physics of it, how can we make a correlation between what happens, in our case of photophysics, that happens on these length scales, or due to the structure in these length scales with the property of the material in the device. This is sort of the fundamental materials question that we're interested in a broad way in this field. And what I'm going to do is I'm going to present this material, which is, I mean, every time, I've been talking about P3HT for like 10 years, and every time I think that this is the last project with P3HT, but it seems to keep coming back, and the reason it keeps coming back is because it is very much of a workhorse. Yeah, thank you very much. In that, of course, there's work going back from well over a decade ago, including from Valley's group on the photophysics of these materials, and it's a very good model system. It's what I would say it's a very good workhorse system, in that we know that there's this sort of, it's a semicrystalline polymer, and a lot of polymers are semicrystalline, but this is a very good model system, in that because of the way that these monomer units are linked together, they're linked in what we call a regioregular way. Chains are able to adopt conformation so that this sort of two-dimensional lamellar crystalline structure can be achieved. And it really can be fairly crystalline. It can also be very amorphous, depending on how you process it. But you've got this sort of structure that has been relatively well characterized. And the issue is that if you go to materials of different molecular weight, their microstructure, their solid-state microstructure can be dramatically different, and it can be very complex. So if you have very low molecular weight, what you end up having is typically a very polycrystalline material. And here you have an arrangement of short chains that can be quite crystalline, but quite disordered. This is because short chains care about what's at the end of the chain. You may have a lot of torsional disorder in the chain, and can be quite disordered. Energetically quite disordered, but very crystalline. If you go to in the limit of a very high molecular weight, very long polymer chains, you can have chains that arrange themselves in a crystalline moiety here, but then can extend, the length of the chain is longer than the length that it takes to have an entanglement, a chain entanglement. So a chain here can extend out from a crystal to a very entangled amorphous region back to another crystal. So these so-called tie molecules are important for transport in this material. For a long time, this was a model system for polymer-based transistors, and really molecular weight played a very big role. High molecular weight was good, and it's presumably because you've got connections between these crystalline domains through the amorphous. But these are very complex microstructures. So now if I'm a polymer or a polymer device person, an engineer or an applied physicist, and I want to make a device, and I've got different materials, and I've got some materials of this molecular weight, some materials of this molecular weight, can I do a very simple spectroscopic measurement like absorption? Anybody can measure with your standard push-button UV-vis type of apparatus the absorption spectrum. I can also, if I have a fluorimeter, measure a luminescence spectrum, and identify the signatures in these steady-state spectra of photophysics that relate to these different microstructures. So that's what we've been working on for quite a bit of time. And the issue is that you can, and the reason that you can is because you can develop models based on very well-established photophysical properties of molecular systems, and so-called aggregate systems. So basically, just to give you a very brief introduction to these concepts of aggregation, these are concepts that were developed really in the 50s and 60s by somebody called Kasha, amongst others, to study molecular aggregates. So if you have a molecule that you can then arrange into a lattice, some type of lattice, that you can arrange it so that it piles in this more or less head-to-tail geometry versus a cofacial geometry. So the molecules are aligned like this versus like this. So there will be, each molecule will absorb light and will emit light. There will be a transition dipole moment associated with each of these units. So if the transition dipole moments align in a head-to-tail way, essentially you can describe this excitation using Frankel type of exciton models. And the idea is that in this arrangement you will have resonance Coulomb coupling. So you've got your transition dipole moments in the molecules that talk to each other. They couple through resonance Coulomb interactions. You form an exciton type of band in which, in this arrangement, the lowest energy is sort of at the center of this dispersion curve. So here, they're molecular systems, so you always will have a bibronic progression the emission spectrum. So vibronic levels in the molecule become vibronic bands, and the transition from the bottom of this, the bottom of the lowest vibronic band in the excited state to the zero band in the ground state is very strongly allowed, and it's more strongly allowed than in the isolated molecule. This is just due to the way that these transition dipoles add up. Yes?
When you get to these resonances,
Yes?
because these things are organic and basically kind of floppy,
Yeah?
you have mechanical changes as well that occur on a like a nanoscale level. I mean, is there like a piezo type effect?
These types of effects won't be very important, but what will be important, because they are floppy and they're very flexible, and there's dynamic sort of disorder. There will be disorder that will be very, very important, and it will be induced by these properties of the molecule. So it will just give you a certain amount of heterogeneity. But these sort of mechanical effects are not very predominant. Yeah. So this is so if you have now some kind of vibronic progression, I'll show you in the next slide kind of what that would look like. But say the molecule will have an emission spectrum with some structure, some vibronic structure, strong coupling because they're floppy, strong coupling between the vibrations of the molecule and the electronic degrees of freedom. So you have an emission spectrum that will have this a very well-defined structure due to this sort of strong coupling, vibronic structure. Now, the origin of this transition is allowed much more strongly than in the isolated or non-interacting molecule by the number of molecules that you have interacting. This is so-called J aggregate. It's only called a J aggregate. There's no physics behind that name. The guy who first came up with that was called Mr. Jelly. So they're called J aggregates. So now if you go to the opposite type of interaction where now you align your dipole, your transition dipole moments in a cofacial way, then due to the symmetry of this interaction, now the bottom of this dispersion band is the highest energy state. So basically you would then, if you relax down to the lowest energy state, now you would have to have an indirect transition to here, and that's not allowed. That's formally not allowed in these materials. It becomes a little bit allowed because of disorder. You break symmetry, slightly allowed, and in fact you can learn something about disorder by analyzing how much of this origin transition you have. So that's what happens. It's not allowed, but the rest of the transition, the rest of the progression is allowed. And this just has to do with where the coherence of this aggregate is, the information is contained. It's in this 0-0 transition. Now with polymers, like I've talked about, you have a hybrid situation in that you've got dispersion along your polymer chain, and due to these resonance Coulomb interactions, you also have interchain dispersion. So you have this hybrid type of aggregate where now you split kind of these bands into multiple bands. Again, you get them, the symmetry such that you get the lowest energy here. But emission 0-0 is still thermally activated because it's from this antisymmetric combination of the two bands. So essentially, it looks like an H aggregate in that you have weakly allowed 0-0 because from the lowest energy point here, you don't have an allowed transition, but it's thermally activated. You can then thermally activate emission 0-0. So this is just a very quick introduction. You can read a review article that we wrote last year on sort of all of these physics. The point is that there are models that are based on very well-established photophysical models of material systems in which you can describe, if you have a crystalline polymeric system like we have, how can we then interpret the absorption and the emission spectrum within these rather well-established models, and then say something about excitonic coupling. Remember, we're very much in the Frankel exciton limit here, but also the influence of disorder. I won't get into the details of the disorder, but let me just elaborate a little bit more on the spectral signatures. So here we have, again, now we have more of a level diagram. Here I have all my my transition dipole moments in the polymer chains that add up to give me now a vibronic band in the weak coupling limit. I'll explain what that means in a minute. But essentially now instead of levels in the molecule, we have bands. So we have this vibronic band, the zero vibronic band in the excited state, the first vibronic band in the excited state. We have similar things in the ground state. Now within an H aggregate, if I excite, so my absorption spectrum will have this vibronic structure exciting from 0 to this 0 band, 0 to the first band, and so on. I will relax, and the bottom, this is the emissive state, in an H aggregate, the bottom state here is formally not coupled to the ground state. So this 0-0 transition is formally not allowed. Then these become allowed. So if I look at the photoluminescence spectrum of the crystal, a polymer crystal, at low temperature, I should see only the 0, 1, 0, 2, and so on in the progression. Here's a photoluminescence spectrum at low temperature. So here we have a very weakly allowed 0, 0 vibronic origin. This is a 0, 1 feature, 0, 2, and so on. And there's a very well defined intensity distribution that tells you to what extent does the molecule need to reorganize in the excited state to relax the new electronic distribution once you excite. And so this is a typical vibronic progression. This emission should have been completely suppressed, but it's a little bit allowed. And it's allowed due to energetic disorder, and you can actually analyze this relative 0,001 intensity to learn something about the nature of the disorder, which is a detail that I won't get into because of time. I do want to get to the 2D spectroscopy. On the other hand, you can take the very same material, so this is a predominantly H aggregate. You can take the same material, same molecular weight, process it in a very different way, so that now the photoluminescence spectrum is dominated by the 0,0 feature here. It looks more like a J aggregate. This looks like an H aggregate. This H aggregate. This looks like a J aggregate. Going back to this nomenclature, sort of a cofacial type of aggregate versus a cofacial versus head to tail. But it's the same material. You do the X-ray diffraction. You still get diffraction peaks that look the same or very similar. So you still have the same crystalline structure. So what happens is just that you can arrange it so that the coupling dominates here between chains, whereas in this processing, the coupling is very weak between chains, but very strong along the chain. And it has to do with how the molecule orders, the chain orders along the chain. So just by processing, you can really induce these different changes. So
I know it uses H and J, Dr. Jekyll.
yes, and so because this is a hybrid aggregate, it's an HJ aggregate. So he has this whole Holstein Hamiltonian that with disorder and Frankel exciton type of picture, and it's this hybrid J aggregate. And he says this is like a Jekyll and Hyde. It's a Mr. Jekyll. It's a Dr. Jekyll and Mr. Hyde situation. That sometimes it likes to be Dr. Jekyll, but sometimes it can't avoid being Mr. Hyde. And so this is the Jekyll and Hyde behavior of polymers. I think we should have called the review paper that, Jekyll and Hyde. And so this will restate what I've just said, but I won't go into details because I want to get to the 2D spectroscopy. Essentially, just to show you that just in a regular film, now going back to this microstructure idea where you've got polycrystalline microstructures versus this two-phase entangled microstructures, the jump between that occurs at a particular molecular weight. In this case, this material for about 50 kilograms per mole, 50 kilodalton, sort of in the polymer lingo. And the spectral changes are very, very pronounced. So your 0,0 relevant intensity really transitions from one regime to another regime, from this microstructure to another microstructure. What we call the Huang-Rees parameter, it's related to how torsionally flat the molecule is to begin with. That also changes, and you can model all of this by Frank Spanner with his Jekyll and Hyde model. He applies the Jekyll and Hyde model and works out. It doesn't show up very well here, but these are sort of two-dimensional coherence function, which tells you to what extent is this Frankel exciton, the the electronic excitation with the vibrational distortion around it, sort of a very exciton-polaron type of situation, to what extent does it delocalize along the chain or between chains? And so you really have a situation where in this short chain limit, what really dominates more is the interchain coupling, but when you go to the long chain limit, the intrachain coupling dominates. And you see the spatial, it's hard to tell here, but spatial coherence is longer along the chain at the high molecular weight limit versus more interchain at the low molecular weight limit. And this is all by modeling the steady state photoluminescence spectra, as well as absorption spectra over all of these different molecular weights. So just steady state measurements, no fancy spectroscopy here, quite a bit of modeling, and you can come up with sort of testable parameters of what the intermolecular couplings are, what the properties of the photophysical aggregate are, and how does that translate into a spatial extent of that exciton. But you notice that they're still very localized. We're talking here about a handful of chains. This spatial coherent goes over 10 chains or something like that. I mean, that's fairly long, but it's still a rather localized excitation. Here it goes along about 20 monomers or so. So they're still relatively tightly tight excitations. So just to summarize, you can change the microstructure. You change this 2D spatial coherence, and you can sort of link that to the spectral line shape. So now,
basically measuring the ratio of the 0, 0 to the
0, 1.
0, 1.
Yeah, and that's a parameter that is predicted by the model. Also, the ratio of 0, 2 to 0, 1. This is the so-called Juan-Ruiz parameter. All of these things sort of are measured, and they can come out of the model as well. This is just to be able to come up with a picture of what the spatial coherence is here within this heterogyte. But then there was this very intriguing paper from John Lupton. This was, I think that here, yes, he's still sort of listing the University of Utah in this paper. So this is a paper that came out 2013, I believe, with really very clean measurements of single chain spectra, single chain emission spectra. So here is the same material, P3HT. I think that the molecular weight that they were using was sort of right in the middle between these two different regimes that I talked about of very polycrystalline versus two-phase microstructure. So they're right in between in terms of the molecular weight. That will be important in how does the chain coil, how can it coil, and so on. But here, what they showed very convincingly was that you can do a lot of measurements of single molecules, and you always find that the emission spectrum, 1, is very, very narrow. 2, it's really dominated by the 0, 0 feature, that the origin of the bibronic progression is very dominant here, so it's very J-like using the Spano language, or whatever this photophysics language. And that doesn't depend on molecule. It's very, very similar for all the molecules that they've measured. But all the molecules that they measured can have an energy ranging over an electron volt over the visible. So enormous heterogeneity in the energy of the origin emission. The line shape does not depend on this energy. Doesn't depend on where it emits, and the line width also does not strongly depend. So here, just to catalog sort of the data, here he's plotting the emission energy, or the 0, 0, the origin emission energy, with the 0, 0 peak position. And so basically, you can catalog them that way. They have the same structure, although they have very different energies over this whole range. Now if you look at the width of the 0, 0 peak, this width of the 0, 0 peak as a function of 0, 0 peak energy, the higher in energy you go, it might get a little bit broader, but notice that we're going from somewhere like 10 electron volts to 10 milli electron volts to 30 milli electron volts. Still very narrow, not very strongly dependent on the energy. And the 001 peak ratio does not at all depend. Now you can then process these single molecules in different ways. You can but through some neat tricks that they played with the processing, they can convincingly show that the molecule is either extended or coiled. When they have the extended chain, it looks like the emission spectrum of solution. Dissolve P3HT in very dilute solution, measure the photoluminescence spectrum, that's this in gray, and they can construct a bulk-like spectrum from single molecules that are extended. On the other hand, if they get them to coil, so that they blend them in PMMA, they look more coiled in this case, then they can construct a photoluminescence spectrum that looks remarkably like the film. This is, of course, not quite as structured as the spectra I showed you in the previous slides, but it does show that essentially if you change the conformation, you can build spectra that look like the bulk spectra, but the shape depends on the conformation. So this is really quite remarkable. So this then leads us to then question whether all this Jekyll and Hyde type of model really is, I mean, that holds up to temperature dependence and so on, but it's an effective model. It's an effective model with effective parameters tested with bulk spectroscopy, linear steady-state bulk spectroscopy. So really, is there really just more of a case of heterogeneity? And so here, that's what they suggest. They say, is the primary photophysics of polyphenols dominated by intermolecular interactions and H-aggregate species? This is Jekyll and Hyde. Or does the material actually adhere to established concepts? By that, they mean sort of whether it coils, it will have this energy or extend it, and so on. So our single molecule experiments tend to favor the latter notion. So basically, they question whether Jekyll and Hyde actually is relevant. And that's a very good question based on this single molecule spectroscopy. So is this Jekyll and Hyde view predominant, or the single molecule view predominant, or the conclusions from the single molecule predominant? What I'm going to tell you is that it's really a bit of both. Now what we want to do is measure the solid state homogeneous line width. So what they have shown is that here these line widths are always very narrow, order of 10 millielectron volts. What would they be in the crystal? So one approach would be to do single crystal spectroscopy, and they are very active in that. People like David Vandenbout as well try to controllably, and that this is a hard part, but get aggregates and then study single aggregates and measure line widths. Even then, you can't, using linear spectroscopic measurements, distinguish between the homogeneous and an inhomogeneous line width. But you would see what the evolution of the line width is as you form the aggregates. But really, our approach will be, let's use a spectroscopic method that will, on the one hand, allow us to measure spectral correlations between 0, 0, and 0, 1 transitions. For that, we have to now go to a nonlinear spectroscopy. I will explain that in a minute. But we can also measure the homogeneous line width as a natural consequence of the fact that we're doing a nonlinear measurement. So let me explain that. So I guess I still have a bit of time to. So now what I'm going to do, again, this is sort of the same type of model that I showed you at the beginning. What we're looking for is if we have this Jekyll and Hyde type of situation where we would have the 0, 0 emission being special in that it's thermally activated, it comes from this point here, the rest of the progression comes from this. But these are two transitions, or when we excite, we can access these two bibronic states if we use a short enough pulse. So what we're going to do is use a short pulse that has a very, very broad spectrum. So now I'm going to make a 10 femtosecond pulse at 2 eV, which is where I need to be here. To make a 10 femtosecond pulse, I need a laser that produces about 100 nanometer bandwidth. Very, very large bandwidth. That bandwidth is enough for me to cover both the 0, 0 and the 0, 1 absorption spectral ranges. So I'm going to excite not very selectively. I'm going to excite everything here with a very short pulse. And then what I'm going to do is I'm going to apply a sequence of 4 pulses. So this is time. First pulse arrives. Second pulse arrives after a delay T21. Then we wait another time, T32. Third pulse arrives. We wait again, T43. Fourth pulse arrives. And then I'm going to measure the total luminescence, the time-integrated luminescence. That's going to be my detected variable. But I'm going to not only control the delay between these pulses, but I'm also going to arrange it so that the relative phase between pulses 1 and 2 is very well controlled, very well defined, and it's going to be modulated at a particular frequency. So I do this by acousto-optic modulation. I have phase modulation effectively. The relative phase of a pulse pair, essentially I have a Mach-Zehnder interferometer in which in it I have 2 nested internal Mach-Zehnder interferometers. I modulate every beam, delay, have 3 delays so that I can control both the delay and the relative phase of one pulse pair and the second pulse pair as well. Why do I need to do that? It's because now I'm going to look for a nonlinear coherent signature. So a photoluminescence that comes through an excitation pathway involving 4 pulses in which I will generate coherences, project them to populations, regenerate coherences, and then regenerate a population to 4th order using this type of a technique, but with a very well-defined phase pathway. Why do I want a very well-defined phase pathway? Because I want to be able to say, I'm looking at this particular nonlinear response, a particular nonlinear response that is well controlled and well understood, that I can then analyze. Sorry?
Polarization.
Yeah, so they can be independently controlled. For the measurements that I'm going to show, they're all linearly copolarized. But I can polarize each of the 4 pulses the way I would like to for various reasons. For the moment, in fact, this would be interesting for this as well to do polarization and isotropy, as I might discuss in a minute. We haven't done that. So this is not something I want to at all describe, but this is just to tell you that we're looking for a particular 4th order response. This is what I call mukamelia. For those of you who know Shaul Mukamel, this is the sort of thing he really likes to get into. It's a language called mukamelia. And essentially what we're going to do is we're going to prepare a response that is to 4th order depending on 4 light-matter interactions with a very well particular phase relationship, each of the light-matter So we create wave packets that have well-defined phase and amplitude that interfere, and the product of the total product of this is what we're going to detect. And we're going to really need to know what the phases were and amplitudes of these wave packets in order to then analyze our signal. So I don't think I want to say more beyond that. Just what you need to understand is that this allows us through, in techniques that are very, very analogous to the spin coherence measurements that I know are done here very, very elegantly. But now in the electronic domain, we're going to want to measure a 2-dimensional coherence function over 2 time variables, T21, T43, at a particular time, T32. So now think of this. I'm going to now explain it in a different way that hopefully will make a connection with other experiments that are done here. And just think of this as a pump-probe experiment. Basically, I'm going to pump, I'm going to probe, but now instead of probing transmission, I'm going to, after my probe, detect luminescence and measure the total luminescence intensity. But now instead of 1 pump pulse, I'm going to have 2, and instead of 1 probe pulse, I'm going to have 2. And because the phase relationship of these is very well controlled and known, I can do essentially an interferometric measurement. I'm going to, in a time domain, construct a spectral measurement. So I'm going to delay these 2 and generate a 2-dimensional nonlinear coherence function at a particular pump probe time. This is a population waiting time. I can delay these 2 pulses to measure essentially my pump probe dynamics. At a particular pump probe delay, I'm going to scan these 2 to measure a 2-dimensional coherence decay function that I can Fourier transform about these time variables to produce a 2-dimensional spectral response. This is at a particular waiting time of 100 femtoseconds. And what's the most sort of boring sample I can do it on? I'll just get rid of my sample and just take the detector straight into the path of the experiment and just measure the photocurrent out of that and show that basically I can construct this total 2D this map that is basically symmetric along this diagonal. So this is really just a silicon density states excitation here and this photoreceiver, and it just gives you this very nice symmetric signal. But now I want to look for asymmetries here and try to learn something from them. So if I go back, and so again, this is a type of experiment we can do. Of course, because it's a Fourier transform technique, it's a time domain technique to extract the spectral information. I have information on real and imaginary components, so absorptive and dispersive components, and that's often useful to know. But here, for example, this is the absorption spectrum of a particular molecule. This is the spectrum of the laser. So over the laser, I'm going to look for correlations of these transitions. This type of thing that we do. But now, if we do take say, the peak signal as a function of T32, this population waiting time, then essentially I'm measuring something like the pump probe decay. So this is just the exciton lifetime, the excited state lifetime. So now I go to my polythiophene system. So now this is the absorption spectrum 0001. This is a laser spectrum. Again, this is my pulse sequences, pulse 1, 2, 3, and 4. I generate a 2D function of these two variables at a particular T32 Fourier transform. At a one combination of phases, this is the so-called refacing signal. It's like what you would have if you did a photon echo experiments. For those of you who are familiar with photon echo or spin echo experiments, it's like the response that you would obtain from a photon echo process. In this refacing response, this is at 500 femtoseconds, so at long times. But what we see, it's very hard to see the way it's plotted with this color scale and also with the projector. But essentially, what we have here are two features that correspond to the 00 and the 01 lines. We also have a broad pedestal here that corresponds to the coupling, the cross peak between 0 and 0 and 01. We excite both 0, 0, and 01, and we can see correlations between these two transitions, and that comes up here. Hard to see with the data the way I've shown them. But the main point is that we have a signal that's very broad along this diagonal, very narrow along this anti-diagonal, real and imaginary. So this is just this is just to drive the point that this is a pump axis, a probe axis at a particular pump probe time.
What is I?
This is the signal. This is the intensity of this signal. This is the signal that we measure that is a function of the pump spectral axis, the probe spectral axis, and a pump probe delay. This is just your signal.
How you're measuring the pump spectrum axis. It's just this lump that you're putting in. This lump of
You're putting in an extraordinarily broad laser spectrum. So over the bandwidth of the spectrum, we're measuring the coherence dynamics. So whenever you do a spectral measurement, if you do it in the frequency domain, there's a line width associated to that. That's where the coherence dynamic information is contained. You can also do the experiment in the time domain and transform it to the frequency domain. But of course, you only have spectral information over the bandwidth of your laser. That's what you can excite. So we're constructing these energy axes through the time domain measurement. But it's a spectral.
What do you measure? Photocolor and photoluminescence?
This is just photoluminescence intensity. But I can measure photocurrent. That's the first slide. I can do this. It doesn't matter how I measure it. It depends on what I'm interested in studying. But here, I want to make this connection between the photoluminescence process and the excitation process. So I'm measuring the time-integrated photoluminescence, just with a regular detector, send it to a lock-in that's referenced to these phase modulation frequencies that I described. So what you should just learn from looking at the spectrum is basically you see essentially what you would see in the photoluminescence excitation spectrum, but now I've dissected it into two axes. I have 0, 0, 0, 1, but I can also see cross peaks. But because of the particular properties of this coherent response, I can also distinguish between homogeneous and inhomogeneous line widths. And so this just to show you that you can do it at different pump probe delays, and you can get a signal that decays, and you learn about dynamics that way. But if you really look at these techniques, I'm not going to get into it because really it would be a bit of a colloquium in and of itself. But for example, this is a very, very nice review that's already a bit old. It's from 2008 from Min-Heng Cho, who is a theoretician very much involved in these two-dimensional techniques. And what you should understand with these types of measurements, these sort of refacing photon echo-like measurements, is that if you have a signal that's elongated like this along the diagonal, you can measure an inhomogeneous line width, but importantly, in the anti-diagonal, a homogeneous line width. So I had to do this rather fancy nonlinear spectroscopic measurement to be able to unambiguously separate the homogeneous and the inhomogeneous line width, which is very difficult to do otherwise. There are other techniques that can do it, but in fact there are also nonlinear techniques like spectral hole burning and so on. That doesn't work very well in these materials, but with this multidimensional spectroscopy you can measure a homogeneous line width. So now if I take the total, the norm of the real and imaginary signal that I showed you before, it's here, and I'm going to look at the anti-diagonal. This is just to remind you of what this all means. Essentially, if you look at the quantum dynamics in an optical transition, so you have got two states here, you pump from 0 to 1, you will have certainly a population decay from here, but you will also have a coherence. And the dissipation of this coherence, you've got a T2 and T1 are these two sort of time characteristic times involved in the process, but in fact the pure defacing is something that we call a T2 star. So basically if you have an absorption line here or an excitation line that's inhomogeneously broadened and it's produced by an ensemble or series of homogeneous line widths, essentially with this technique we can measure this gamma or gamma star, the homogeneous line width versus the full inhomogeneous line width. And so this is just to say that I didn't feel like drawing this, so I just ripped it off of this paper, which has nothing to do with my talk, but I just like the cartoon, so I ripped it off from that. So now if we do this, essentially, strictly speaking, only at 0 time, at 0 population time, 0 pump probe time, this is where it's truly a homogeneous line width, but I mean, in fact, it doesn't seem to evolve very much with delay. If we look at this anti-diagonal, we're measuring an homogeneous line width of about 140 millielectron volts. 140 millielectron volts in this microstructure. In fact, we've done it in different microstructure, and there is a microstructure dependence, but it's always above 100 millielectron volts. It's never down to the 10 or 30 millielectron volts.
What is the laser width?
The laser width is quite a bit broader than this. It's I don't know. It's what is it? A 2eV 100 nanometers. It's very broad. In fact, our measurement. Well, here you can see it. This is the inhomogeneous line width, and it is limited by the bandwidth of our laser. Of course, you know the absorption spectrum of P3H is much broader, so that is limited. But this is not. This would be limited by the pulse width, which is of course related. But here we have enough time resolution to measure this narrow line width. We have about 10 femtosecond pulses. And so when you compare this, in the isolated chains, in this very intriguing paper by John, they were measuring gammas of the order of 5 millielectron volts, maybe 10, or not, yeah, maybe 10, but really somewhere between 5 and 10. So this translates to a pure defacing time of something like 830 femtoseconds. So with the 140, the 2 gamma being 140 millielectron volts, that corresponds to a defacing time of about 50 to 60 femtoseconds. So this is quite a bit faster. So the defacing dynamics, what determines defacing in these systems? So generally you have an optical transition that is not isolated from the universe. It has an environment to which it's coupled, and the way that it's coupled to this environment determines these quantum dynamics. So if you change the environment, if you change the coupling of the two-level system to its environment, you're going to very significantly alter this defacing time. So now you're looking at an isolated chain in a matrix, but in an inert matrix, the pi electrons in the polymer chain are not interacting with other pi electrons. They're sort of, in this way, interacting with a particular system, but a lot more isolated than they would be in a crystal. When you're in an isolated system, or a less strongly coupled system, these effacing dynamics will be very long. Now you put it in the crystal where the pi electrons know about pi electrons in other chains, then all of a sudden your environment is very, very different. The quantum dynamics are going to be such that you're going to dephase much, much more rapidly. And so this shows that really the bulk behavior cannot that cleanly be explained either just from an ensemble built from single molecule measurements. But it's still a very intriguing and interesting question. Why do the line widths change so much between the single molecule and the crystal? And I think that's a very interesting open question that I'm going to have some conversations with John about to see if we can do something together to address that in a more quantitative way than what I've just said. I mean, I've sort of hand-waved an explanation here. And so what I'm going to do now is summarize essentially what I've talked about, these two different ideas, two different results really, or two different approaches. One from the single chain spectroscopy, the PL line widths are very, very, very narrow. The idea is that because you have such heterogeneous system, that you have such broad and homogeneous distribution of PL energies, that really do depend on how the chain conformation is. This really is a very predominant consideration in bulk spectral line shapes. Whereas this sort of Jekyll and Hyde view is different, of course, in that effectively, even when you consider disorder, which can be quite high, you can still sort of define excitonic couplings and so on that really define excitons essentially in a solid state sort of way. And so with this Jekyll and Hyde sort of picture, you would come up with a different interpretation of the spectral line width, but the homogeneous line widths are very, very different in the way that you would expect in going from like a single molecule to a solid state system, in my opinion. So with that, I would like to end. Basically, this is the work of the early part of the talk was Francis Paquin, was a PhD student in my group, graduated last year, and now is working essentially for an optics company. But the 2D spectroscopy was set up by Pascal, Grégoire, Eleonora Vela, a very talented PhD student and a postdoc in my group. Claudia is also a postdoc who's done a lot of the processing in this project. Very important collaborations, Frank Spano, his student Haj, Natalie Stinglin, who is, you notice Imperial College everywhere basically. I did my sabbatical there and I have a visiting professor appointment there largely because of my collaboration with Natalie Stinglin in this type of a project. And she had a postdoc. Natalie's a polymer scientist. She really is a plastic person. Now she did her PhD working with, plastics. And I'm an ultrafast spectroscopist. And so we really didn't talk the same language at the beginning, even though we shared an office in Cambridge. We wanted to collaborate since we were both in Cambridge, and never happened. But then Gianluca was a physicist who could talk the plastic language. Working with her, spent a lot of time in my lab, and that's what it took really for us to be able to do this type of work together. And very sadly, he died a couple of years ago from a very unusual condition he had, and so that was a very big loss for us because he really contributed a lot, but he was very involved in the early parts of this project. So with that, thank you very much, and I'm very happy to discuss.
I want to make a comment. When I started picosecond spectroscopy, it was 1979, and picosecond laser were invented by Eric Gibbon and Shan at Bell Labs, John Lewis. And when we did spectroscopy, we were very careful that the pump and probe wouldn't overlap in space, time, and energy, because then we call it coherent artifact.
Yeah.
Now, 35 years later, this is coherent artifact. This is its whole talk and physics of coherent artifact. But for us, it was dead.
Yeah.
We didn't want to. It did coherent artifact very well. Thank you very much.
Except for here we try to extract information from it. So.
Yeah, I didn't know it that time.
Yeah.
Okay. Any questions, please?
So how do we understand this alignment then? Is this the exciton is jumping from one molecule to another, or kind of partly jumping, or what's going on?
Yeah, so this, if you're asking within sort of the Jekyll-Hyde view, yes, you've got this two-dimensional spatial.
Let's think about just two molecules.
Yeah, so let's think about two molecules that are aligned cofacially, but they also are long enough that they have some coupling along the molecule itself.
Right, right.
And so you can think of it as an excitation that's hopping between these two. That will determine, but by excitation here we mean not just the electron, but really the electron and the vibrational distortion around it. This is very, very, like sort of a polaronic type of thing. That's sort of coherently shared between different sites. And you can think of it that way along the chain, except that now, at least the way you would model it, it would be more of like a Mott type of, where you have the electron in the hole. If you want to talk in that language, it's limiting sometimes because it's, going from the sort of the solid state physics sort of to the molecule is sometimes a bit confusing. But let's say that you've got your two particles that make your excitation localized in one molecular unit, and those things being coherently sort of shared along the chain. So that's how you would sort of think. This two-dimensional exciton coherence function would be sort of to what extent you've got these effects. Yeah.
So why does this broaden it?
Because there is disorder. There's a large and homogeneous. Yeah, I mean, this is the messy part that you were talking about at the beginning, is that you throw in disorder, and each side will have a different energy.
But it's a kind of a local disorder, so it isn't really inhomogeneous. It's like locally.
Yeah.
It isn't like this pair is different from that pair that makes it inhomogeneous.
It would be that this pair is different than that pair because the molecule in which this pair is sitting will be twisted like this, and the other molecule will be twisted a little bit differently. And the energy, there's a very strong coupling between the electronic degrees.
Inhomogeneous.
Right, that's what, yeah. What's a homogeneous line? Yeah, because there is a defacing process. There's a quantum defacing process, and that means there's a line width, and so this time frequency.
No, I get it. I just don't
Yeah.
think what's doing the defacing.
It's because the system is talking to its environment, and it's losing the coherence information through that. Yeah. Sorry.
I'm of course fascinated by your pulse sequence. What
Yeah.
else could I be?
Sure.
That is of course the so-called COSY, the
Yeah.
correlation spectroscopy, as
Right.
it's been used for
In NMR,
for
yes.
NMR
Yeah.
technique.
Yeah.
So you mentioned, of course, that these pulses have to be mutually coherent. You mentioned that. Are they actually in phase, or do you actually have, let's say, something like a 180-degree switch?
Yeah.
And so my other question is, can you apply, or do you even use phase cycling?
Yes, that's a good question.
Sequences.
Yeah, good question. There's two ways that we can do this experiment. Either by defining the phase, but then we have to work really hard that this phase information is not lost in our experiment, because unlike NMR, here we're talking about phase stability that we need to very, very high degree, something like lambda over 100 or something. So, we're in a building that's probably quite a bit older than this building. My lab is in the 4th floor. I've got the undergraduate cafe down the hall. These guys like to ride unicycles down the hallway. And I need to do this interferometric experiment to very high. So instead of my mounts, having to prevent my mounts from doing this to lose this high degree of phase definition that I need, what we do instead is do this 180-degree phase modulation. And so I only need to, the way this experiment is done at the moment, I only need to have very well-controlled phase information between each pair. And so what I do is I generate the pair in the Mach-Zehnder interferometer. So I can delay one of the arms with respect to the other. And I have acousto-optic modulators in each arm so that I can modulate both, such that the relative phase will be doing an 180-degree switch at some kilohertz rate. But then I'm going to make sure that that frequency is different for these two pairs. So then I can detect my luminescence, and with a lock-in, select the component that is at a combination of these two phase modulations. For these non-refacing experiments, it's a difference of the frequency of the phase modulation. I can also measure the sum simultaneously. And so there's two ways of doing it. You could either phase cycle and arrange your experiment so that at least all the path of every single pulse is common. Then you can phase cycle and control the phase this way. But this way is through phase modulation using a lock-in amplifier. Yeah.
I noticed in your data that you plug energy, so that's the energy for the quantum and the probe.
Yes.
So you do have two colors, right?
Well, you have the same color for each pulse. So basically, you've got the same, through the same node by the same laser, we generate the output that we split into these 4 pulses. So it's the same bandwidth. Now, we could do a 2-color experiment where pulses 1 and 2 are a different source, and pulses 2, 3, and 4. That could be done. We haven't done that. Yeah. Yeah.
But so the Sarah will ask you another question.
Yeah.
If you measure, other than photoluminescence, you measure magneto-optics, can you generate some, can you extract information about spin dynamics?
Yeah, so for example, in semiconductors, for example, we could have circularly polarized. We can prepare a particular polarization state for each of our pulses, and through different combinations, we could do those types of experiments, I think.
Has been done?
It's been done not with this type of implementation, but similar ones by, for example, Keith Nelson, who's done a lot of gallium arsenide quantum wells. Yeah, and there he's interested in multi-quantum coherences and all kinds of things.
Yeah, so I've worked with piezoelectrics.
Sure.
I'm kind of, when I talked about like acoustic and mechanical vibrations earlier, that's kind of where I'm coming from.
Sure.
These materials are, you talked about also acousto-optic techniques to use for changing the polarization.
The phase.
The phase, rather. So these materials, I'm assuming that they have resonant frequencies that are, really high, like terahertz range and whatever, as opposed to, acoustic resonances, right? So if you pump these things acoustically as well as optically, is it possible that the acoustic resonance would cause these, the disorder that's present within these floppy crystals, quasi-crystals, organic molecule, to maybe, reduce and give you a better exciton response when you drive it with the laser pulses?
Yeah. So let's say that...
I'm just curious if you played with that at all.
No, I don't think anybody's really played with that. So I think what you're suggesting is if, there's this... It's not really a phonon here that we would have to discuss, but rather a localized vibration. If you could control that vibration in such a way that it will decouple it from the electron, could you really get rid of a lot of this sort of type of fast quantum dynamics? Maybe. That seems like it would be a very, very hard thing to do just from the frequency of these modes.
Right.
But that would be an interesting sort of something like a Brillouin type of excitation, but of course not phonons. But
let me translate what you just said. You see, your pulse actually excite 0, 0, and 0, 1.
Yeah.
So there is a vibration there.
That you excite. Yeah.
Do you think that this has some bearing on the coherence time?
No, not in the pure defacing time, because the reason you excite with such broad bandwidth is to look for cross terms, look for the cross couplings between. But the homogeneous line width should not depend on your on your laser bandwidth. So as long as you have the resolution to measure the line width, so if you have enough bandwidth to measure the homogeneous line width, then it wouldn't matter you can excite the whole thing over the whole visible if you had such a short pulse, and you would get the same homogeneous line width from this technique.
Any other questions? If not, let's thank the speaker again. Okay, so
I don't have a call.
Spatial map is which one? The 9 to 9. 9 to 9. Okay, 9 to 9. Okay, see you.
75
You keep learning things.
Yeah, that's really cool.
Thank you. Yeah. We'll chat more later.
So basically, so each of these pulse pairs, what you produce is essentially a rotary echo.
Exactly.
Yeah, so
exactly.
right, okay.
Yeah.
Very good. Okay, I get it now. You're very excited.
Yeah.
You can measure thermometry. Thank you. Exciting.
Yes.
You make it. Seems like you're excited.
Thank you.
Talking about the board concavity, so you're interested in doing some of the same measurements and stuff, because you should definitely see the change in the
There you
coherence
see a lot of cross
of the interaction.
The thing is that there, because you know what the dispersion is, you can calculate the type of machine we showed. Then instead of plotting this as energy, to the energy spectrum, you can measure the momentum correlation. And then say, okay, if I prepare a polarity of this particular case state, how does it correlate with all the other Ks to give me my K equals 0 sigma? My ground state. So that's the kind of things we actually
Cool, yeah. Neat. I'll look forward to the publication. Let's get to you. Safe travels.
Great, thank you very much.
I do want
At what time? My flight is at noon, I think. Let me see, let me make sure. My flight is at 12:20. So I don't know, it's not a good
So 5:30 will be good.
10 makes sense, you think? That's plenty of time.
Yeah, if you want, you can come and take you.
Great.
Mazda.
Fortunately, it's not so early.
It's 9 and 9. 9 is 9.
I guess.
Thank you very much. Because I have to bring the speaker in any case.
Oh, okay.
So why don't you come with me?
Is he staying at the guest house?
Yeah, he's staying.
This is the.
So 5:30 in my office.
Okay.
I bring you
I will
here.
be back.
You need a right way.
Yeah, so I need to go to the hospital after there.
No problem. Because
Oh.
Because I need to
So
pick up
that's
some
okay.
conference.
Oh,
so wait for you. You can come.
Okay,
Thank you.
I will be back in a second. Nice talk. I just have a question for you.
Sure.
I'm not a
Yeah, that's
physicist,
fine.
but
It doesn't
more.
matter. This is not physics. This is optics.
So I have more of a fundamental question from a chemistry point of view. Are you inducing oxidation of these P3 molecules by heating them up? Or they're just like as gas? Because I mean, as gas, like as soon as they film, it's still gonna have some sort of, orientation. But you can further induce orientation.
Yeah. These are wire barcoding. These are wire barcoding from
Mapping.
but all of them processing. We've also then done annealing and then look at the whole series again.
Okay.
And we do see some clear effects of that. Yeah.
So, how about, can this be translated to small molecules?
Yeah.
So what would be like the difference between having a polymer and a small molecule.